Hey everybody, so in this chapter we're going to talk about exponentials and logs, which kind of goes naturally with the inverse function stuff that we talked about. Okay, the first two sections should totally be review for you guys, so we're going to go pretty fast and we're hopefully just going to review some stuff that you're already familiar with. Okay, so just to remind you, the definition of an exponential function . Okay, is something that has this base form. Okay, now obviously it can be transformed from that, but this is supposed to be the base form of this function. And what really makes it an exponential is that you have the variable in the exponent. Okay, so remember A is the initial amount. Okay, and then B is called the growth or decay factor. Okay, so if b is greater than 1, it's exponential growth. If b is less than 1 but bigger than 0, then it's exponential decay. Okay, all right, so let's do an example of solving some exponential equations. Okay, and we're going to talk about the two easiest solving method for exponential equations. Okay, so for this one, we're going to use what's called the equating exponents method. Okay, and the reason we're going to do this is because we can see that here we have 3 and here we have 27, and those are both powers of 3, okay? So whenever the bases could both be written as a power of the same number, the equating exponents method is usually easy and pretty fast, okay? So if you can rewrite both of the bases as the power of the same number, then this method usually works, okay? So what we want to do here is we're going to rewrite them both as powers of 3. So this is already written as a power of 3. And here I'm going to rewrite this 27 as 3 cubed. Okay, and now I'm going to simplify using my exponent rules. So I know that I need to multiply these, and I'm going to get 3 to the 3/2 power. Okay, so that's the setup. Now what makes this equating exponents is we have the same base to two different exponents, okay? And we can say, okay, well that means those two exponents are the same, okay? Now the reason that we're really allowed to do this is because exponential functions are one-to-one functions. So there's no way to input two different exponents and get the same answer out. Okay, this method doesn't work for a lot of things, like for example, x squared. If you had x squared equals y squared, okay, that doesn't mean that x is equal to y, right? So you can only use this method with one-to-one functions, and because exponentials are one-to-one, we are allowed to do this, okay? And then we'll finish solving by adding 1 to both sides, okay? All right, so there's our answer, and this is our equating exponents method. All right, so let's look at another example. Okay, so before we can actually use the equating exponents method, what we want to do is isolate the exponential part. Okay, so I'm going to subtract 2 from both sides. Okay, and then I'm going to divide both sides by 90. Okay, now we're going to try to write both of these as powers of the same number, okay? So if we have 2 and 4, it makes sense to write them both as powers of 2. So this is 2 to the first, 4 is 2 squared, okay? And then we're going to use our exponent rules here to simplify. Okay, and now this is the part that's equating exponents, so we're going to set our exponents equal to one another and then finish solving by dividing by 2. Okay, all right, so it's important when you're using the equating exponents method that you are isolating the exponential part first, okay? And the reason we didn't have to do that in the other one is because they were already isolated. All right, let's try one more example. Okay, so here we kind of already have the exponential part isolated. Okay, this stuff, you can't isolate everything, right? So you really want to isolate the exponential part, so that is isolated here. Okay, and we're going to choose what thing we're going to write everything as a power of. So we have 2, root 2, and 16. So we're going to write everything as powers of 2. So this already is a power of 2. That's a 3x. Okay, now how do you write root 2 as a power of 2? Well, this is 2 to the 1/2 power. Okay, and 16 is 2 to the 4th. Okay. Now, just like before, we're going to use our exponent rules to simplify this, okay? So we're going to subtract our exponents, okay? So 1/2 minus 4, okay, is going to be -7/2. Okay? And you do want to do that instead of putting 1 over 2 to the 7/2, because we're trying to get them to both just be 2 to some power, right? That's our goal. Okay, so now we can set our exponents equal to one another, like this, okay? And then we're going to finish solving. Okay, and this is our final answer, x equals -5/6. Okay, so let's look at some examples of situations. Oh, we'll do one more example like this before we move on to a different type of example. Okay, I wanted to do this example because in this case, you can see that you don't have to use either one of the bases. You can use a completely different number. So to me, when I look at 4 and 8, those are both powers of 2. So I'm actually going to rewrite both of these as powers of 2. Right? So instead of trying to write 4 as a power of 8 or 8 as a power of 4, okay, I'm just going to rewrite them both as powers of 2, which is pretty easy. Okay, using my exponent rules to simplify again. Okay, and now I'm going to set my exponents equal to one another. Okay, combine my like terms. Okay, by subtracting 2x from both sides and adding 3 to both sides. Okay, and then I'm going to divide by 4. Okay. All right, so now let's talk about a different type of exponential equation, one where you can't really use equating exponents. Okay, and we'll see why in a second. Okay, so if you look at this example, we have the exponential part isolated, which is always the first thing you want to do in exponential equations. Okay, then normally we would try to write these both as a power of something. Well, 10 is really only a power of 10, and 1/3 is definitely not a power of 10, right? We could write this as a power of 3, but you can't write this as a power of 3. You can write this as a power of 10, but you can't write that as a power of 10, okay? So that means we can't use equating exponents, right? So we tried using that, doesn't work, okay? So our next choice is to use logs, okay? So we're going to use log base whatever this is, okay? So this is 10 in this case, so we're going to use log base 10. Okay, now here you can't simplify log of 1/3. I mean, you can a little bit, but we're just going to leave it like this. Okay, and here you absolutely can simplify, right? Log base 10 of 10 to the 2x plus 3 is 2x plus 3. Okay, so that allows us to finish solving this by subtracting 3 and then dividing by 2. Okay. So it's important to point out that there's no way to simplify this expression other than to use log properties here, which you're welcome to if you want to, but you don't really need to in this example because it doesn't get a lot simpler than this. Okay, so the most important thing is that you guys don't try to combine this with this or somehow combine this numerator with 2, right? These are unlike terms. There's no way to combine them, so you would just leave your answer like this. Okay, so that's the basics of using logs to solve. So let's see one other example of when you might use logs to solve. Okay, so here we go. The first thing we're going to do is subtract 1 from both sides. Okay, and then I'm going to divide both sides by -12. Okay, and you need to do that because you always have to isolate the exponential first. You can't do anything else. Also, I wanted to point out that you can't subtract these, okay, for the same reason that you can't subtract them when you have something like this, right? The 12 is part of this expression, which is not like terms with the 1, okay? So for that same reason, you can't subtract these two numbers, okay? Now, I'm going to use logs here. Okay, and I'm using the natural log or log base e because I already have base e. Okay, there we go. Now natural log of e to the 4x is 4x. Natural log of 1 is 0. Okay, divide both sides by 4, and I get x equals 0. Okay. All right, so there's my two methods for solving exponential equations. You can either use equating exponents, which I usually try to do first, and then if that doesn't work, I'll use logs. Okay, so like I said, this is really a review. I will send you guys some resources if you're feeling like this isn't enough of a review, but we're also going to review in this section some graphing. Okay, so let's go over the key features of the graph. Okay, so for something that looks like b to the x, right, a base graph type of graph, okay, we're going to have a horizontal asymptote which is not cross at y equals 0. Okay, so this graph doesn't cross the horizontal asymptote, although we know it can sometimes. Okay, so it doesn't cross the horizontal asymptote at all, and it's at y equals 0. Okay, and then we have our key points. Okay, and there's 3 of them. So we have -1, 1 over b, Okay, then we have 0, 1, and we have 1 comma b. So the key points really depend on the base here. Okay, and if you can't remember them, you can tell that these are just what you would get from plugging in -1, 0, and 1 for x. Okay, all right, so additionally, okay, remember that for y equals b to the x, the domain, okay, is everything, okay, and the range is going to be 0 to infinity. Okay, because b is a positive number, you can't get a negative number with an exponent. Okay, so this is going to be our domain and range for this function. Okay, so that does affect what the graph looks like, but you don't need to draw that in any way for the graph. These are the things that you need to draw when you're graphing. Okay, so let's do some examples of graphing. Okay, so we're going to graph two base graphs here. Okay. Okay, one with b greater than 0, so or greater than 1, so we're going to have exponential growth, and one with b less than 1, so we're going to have exponential decay. Okay. All right, so our key points are going to be -1, 1/2, 0, 1, okay, and then 1, 2. Okay, so we're going to draw in our horizontal asymptote here. Okay, and then we're going to graph our three key points. Okay, so -1, 1/2, 0, 1, and 1, 2. Okay, and if you remember, the base graph looks like this. Okay. All right, so for 1/2, our points are going to be -1, 2, 0, 1, and 1, 1/2. Okay, so we're going to draw in our graph here. Here's our horizontal asymptote. Okay, so for the base graphs, it's always at 0. Okay, so we have -1, 2, 0, 1, and 1, 1/2. Okay, so this is the general shape for exponential growth, and here's our general shape for exponential decay. All right, so we're going to keep those, and let's look at some examples of transformations. Okay, so our first base graph, or yeah, we're going to use our first base graph here, okay? Okay, so here this +3, that's inside the function, so that's going to move our graph left 3, okay? And this minus is going to move the graph down 1. Okay, so here we go. Okay, now we're going to show our horizontal asymptote being moved down 1, like this, okay? And then we're going to graph all of our key points, okay? So normally we would be at -1, 1/2, so we're going to move down 1 and left 1, 2, 3. Okay, normally we'd be here, so we're going to move down 1 and left 3. And then normally we'd be here, so we're going to move down 1 and left 3. Okay, and our graph is going to look like this. Okay, so you can see compared to the base graph here, right? This is what our base graph looks like. That's what our shifted graph looks like. Okay, let's do one more with this base graph. Okay, So this negative x is going to reflect the graph, okay? And it's going to reflect it left and right, affecting the x coordinates, which is across the y-axis. Okay. Then we're going to have this plus 1, which is going to move the graph up 1. Okay, and just remember, you actually have to do these ones in order because they're both affecting, oh no, they're not. I guess you could do them in whatever order. They're affecting different coordinates, right? This affects x, this affects y, so the ordering actually doesn't matter. Okay, so let's look at our graph here. Okay, so I'm going to start by labeling my horizontal axis, or my horizontal asymptote, which is going to be here at 1, right? We've moved it up 1. Okay. So normally I'd have this point here, so I'm going to reflect it across and move it up 1. Okay, then I'd have this point here, reflect it across and move it up 1. Normally I'd have this point, I'm going to reflect it across and move it up 1. Okay, so there's my reflected graph that's shifted up 1. Okay, let's look at some transformations of the other base graph. Okay, so this 3 is going to stretch it vertically times 3, okay? So remember, that's going to multiply all of the y coordinates by 3, okay? So I'm going to put in my horizontal asymptote, right? 0 times 3 is still 0, so it's still at 0. Okay, so normally it would be at -1 1/2, so we're going to be at -1 3/2. Okay, 0 1 moves to 0. Oops, I'm sorry. I was using the wrong base graph. Okay, so normally we'd be at -1 2. So when we times that by 3, we're going to get -1 6. Okay, normally we'd be at 0 1, times it by 3, we're going to be at 0 3. Okay, and normally we'd be at 1 1/2, and we're going to be at 1 3/2. Okay, it's really important that you still draw your graph going all the way down to the axis, okay? It still goes down to the horizontal asymptote, even though it's stretched out, okay? So don't show it like flattening out up here. You do want to show that your graph goes all the way down towards the horizontal asymptote, okay? All right, one more transformation of this guy. Okay, all right. So our transformations are going to be reflected across the x-axis, okay, because of this negative sign, and then the +2 is going to move it up 2, okay? Now these do both affect the y coordinate, so we're going to do the reflection first and then the shift, okay? All right, so let's look at our horizontal asymptote. So it should be at 0. When you reflect it, it doesn't move, and then we're going to move it up 2. Okay. All right. So this point that should be at -1 2, we're going to reflect it, and then we're going to move it up 2. This point should be here. We're going to reflect it, and then we're going to move it up 2. Okay, and then this point that should be at 1/2, we're going to reflect it, and then we're going to move it up 1, 2. Okay, so the graph is going to look like this. Okay. All right. So I hope that reminds you guys of these basic facts of exponential functions, and the next section is about the basic facts of logarithmic functions. I'll see you guys soon.